Yeah, trying to keep a particular watch when I go to this. I don't know how well that's going to be showing up, but at least the size should be good. It'll just be a matter of waiting. And I've already got it started.
Okay, so the reason I'm going to return to the homework back in the last 5 minutes is so that I make sure that today's lesson, we're stopping at a good point to say, for this new chapter we're starting, chapter 18, where we cut off today, that's as much we'll go on the test, and then we'll finish up that chapter and a related chapter in the 2 days next week, review Friday of next week for the final. There's the attendance sheet to go around.
Chapter 17 is a review.
17 is a review chapter, so I might pick some examples out of there, or maybe a test question might come from there, but it is not something with new stuff. I do want to tell you though, when I pass back to the homeworks, that there were quite a lot of 5s that could have been 6s. And the reason primarily was because at the very end of the first 2 questions, the author asked something like, does this provide significant evidence that blah? So very quickly here, if you fail to reject the null hypothesis, that is equivalent to saying that there's not significant evidence in favor of AJ. There's that one question about trying to pull apart a certain type of wood, how many pounds or something had to be used to do that. And it might have been a matter of there is not significant evidence that for the mean of all blocks of that type of wood, that it was different from 31,500 pounds, something like that. If you do reject H0, that's equivalent to there is significant evidence for either your one-sided or two-sided alternate hypothesis. So if people were stopping with fail to reject H0 or reject H0, taking a close look at the very end of the paragraphs, what the authors had there. You know, for the first 2, you might have lost 0.5 just because of not then answering his question, is there significant evidence or not? That's why a lot of people got 5s when they could have been 6s. On the test, that kind of thing wouldn't hurt so much because I'll put more weight to the earlier parts of the question. But when it's only out of 2 points on the homework, even a small part brought you down to 1.5. Alright, so I already sent this information out by an announcement on Blackboard last night, and maybe you got a copy of that in your email. If you didn't already pick up one of the review packets, pick one up on the way out when I'm handing the homework back to you. The chapter we're doing today, again, there's most likely going to be something left of it. You do have it the test, which would mean I'll only put a certain amount on the test then. But chapter 18 and 19 are going to look at some more realistic conditions. But beyond that, with a few changes, we're doing the same things we were doing in chapters 14, 15, and 16. confidence intervals, and hypothesis testing. So a lot of this stuff is going to stay the same, a few minor changes to fit the more realistic conditions. What were the three conditions? One of them was that we don't know mu, but we do know sigma. What are the other two? Got a normal distribution?
SRS.
And a simple random sample, okay? As we found in chapter 16, there are some cases where, hey, if you can't get a simple random sample from, say your population of interest is U.S. adults, which, by the way, people can say, that is my population of interest without that being a bias. They want to know something as trivial as what's the mean height of adult females, then since kids are still growing, they can choose to not get information from those under 18. Well, say you can't get a simple random sample that's coming from the entire population. You could, however, get a simple random sample out of the few thousand people we have here, because there's no reason to believe, except maybe for our basketball players, that college students are any different from the rest of the population in regards to height, right? So you'd be narrowing your population down to a sampling frame and then getting a simple random sample. We were talking in chapter 16 about those times when you could say, well, it should still be representative. So we can act as if we do have a simple random sample from the population. We're still going to need that. Still very important that either it is an SRS or that we can regard it as an SRS. Normal distribution. We still want that, but really normal distribution is an ideal, perfect kind of distribution that probably very few things actually meet. But if we have at least something that's symmetric and single peaks, we'll probably still get away with doing what we're going to do in this chapter. But that last bit about not knowing mu, but we do know sigma, as I said before, is strange. If you think back to chapter 2, how you compute sigma, or S is a square sample. Either way, to get S, you need to know X bar. To get sigma, you need to know mu, in the way we taught to calculate it. So that was weird. So what we're going to do, as it's listing on page 437, still, we have an SRS, or we can regard what we have as an SRS. Either we have a normal distribution, or at least it is single peaked and symmetric. But the more realistic situation, the third thing was we don't know mu or sigma. In place of sigma, we're going to have the formula that will have S from the sample. Instead of using a population standard deviation that we probably couldn't get anyway, we use the standard deviation from the sample, little s. You can see that stuff on page 437. So instead of calling what we're doing Z procedures, Z-scores going with normal distributions, what we call our variable here, when we don't know sigma, we'll be using S. They call them T-scores, and we'll get T distributions. To be honest, I don't know where the letter T was chosen from, but let's go with it. Z is back there, T here, okay. Draw a picture here to explain this bit. Remember when you have larger Z-scores, what happens to the probability when you have a larger Z-score? Think about what we had on table C, which is right there. As we get bigger Z stars, what happens to the probabilities? for either a one-sided test or a two-sided test. They're decreasing, okay? Well, remember this formula for the z-score. If we don't know sigma, then what we want to do, so that we are being, not politically, but statistically conservative, you do not want to reject the null hypothesis if that, here. Okay, remember these local jug mugs. This one is supposed to be 20 ounces. If you bought 20 for friends in the course of a year, and you kept finding that they would only fit 19, you could then go get yourself a simple random sample and conduct a test, where the null hypothesis is mu equals 20 fluid ounces, and the alternate would be that mu is less than 20 fluid ounces. Suspected at first from the previous one, so now go do the rigors of the testing. Well, what's going to happen if your test says that you have significant evidence that it is less than 20? You'd be rejecting the null hypothesis. You let Loaf and Jug know, hey, you're ripping this off, right? They better go check it themselves, right? They'd look at your work and say, okay, now we're going to go try it ourselves, maybe get a bigger sample. What's going to happen if they reject it as well, and it turns out they made the wrong decision? Maybe they just got, even if it was a sample of 1,000, there's still that room for error, right? If you have alpha at 1%, what would be their chances of being right when they reject H0? What percent can go along with 1%? 99%. So if they're rejecting the null hypothesis, their confidence interval that would be related to in a two-sided test would be a 99% CI, and they'd be looking to see if the mean's in there or not. Okay? So, as you found on the last question of the homework, if it's outside, then they can reject in a two-sided test. Well, maybe it just happened to be that rare sample that misled them. Actually, it does have a mean of 20 ounces. Now they've just rejected, and they start retooling things which could cost thousands of dollars or whatever to produce it right, when in fact it was right all along. Am I making my point here clearly? As to the consequences of rejecting H0 when maybe you shouldn't? Am I making that somewhat clear? Okay. So, now when we don't know sigma, what we want to do is, so to speak, thicken up these tails here so that you have to go even further out to have an extreme score. Our t distributions are going to be set up so that all of them have more out here in the tails. You have to go further out to have that low probability. That's what I'm talking about of being more conservative in a statistical sense. The reason for this, if you're going with the standard deviation of the sample, S, instead of sigma, it has less variation anyway in a sample. Remember, there are many normal distributions depending on mu and sigma. So here, that's still going to matter, but another thing that matters is the sample size. That's why there are multiple distributions. Where I say there, look at 439 and 440. I've got it on the next slide anyway. 3 things you need to know. Do you remember when we calculated standard deviation in chapter 2? Before we took the square root, we divided by something. It wasn't n. Do you remember what it was? N minus 1. In a sample, there's some missing information. We don't have the entire population. So we're subtracting this by 1, and that gives us something called degrees of freedom. That's going to affect when we look at the upper part of table C. Instead of a Z star row, we're going to use a T star row, but it's going to be related to the degrees of freedom using n minus 1. Sample size minus 1 will give you degrees of freedom. And then the other two things, the confidence interval will still be x bar plus or minus the margin of error. But instead of Z star, we'll have T star. Put one of those rows there. What did we used to have? We used to have Z star times what? Sigma over square root of n. So here's the S over square root of n. And as for your test statistic, the way we calculated Z was written up there. For testing, so Z we've got T. It'll still be x bar minus the claimed mean all over sigma S over square root of n. Just like we replaced sigma there with S. Here we replace sigma with S. Otherwise, it should look pretty similar to what we've already been working with. Real quick, in this chapter, you're going to see a term, standard error. That's not the same as standard deviation. And if I remember correctly, when I was working on trying to get that PhD, I was actually doing research not in math or in statistics, but in math education, the teaching and the learning of it. And there's a fair amount of statistics to know about. And the reports I read, somebody else's journal articles, they may sometimes refer to standard error from some sample instead of their standard deviation. So I'm going to tell you what that's equal to, and we're going to use it in Apply Your Knowledge 18.1 on page 438. So S, little s, is our standard deviation for a sample. The standard error for the sample is just S over square root of n. Page 438. There you go. Erase it. Standard error, or SE for short, is S over square root of n. And in this particular problem, we're told that the study of commuting times reports that travel times to work of a random sample of 1,000 employed adults, they had a mean of 49.2 minutes, and the standard deviation is S equals 63.9 minutes. So what's the standard error? S was 63 point what? 9? Okay. They didn't write n equals, I don't think, but we were given what n is supposed to be. Which number was the n?
1,000.
1,000. Okay, so divide by these square roots of 1,000. And unless you're not doing anything else with it, which is the case here, but if I had to use that as part of some other bigger calculation, I would hold off on rounding. I would not round yet. On this one, let's say we go to the nearest 100, even though the authors did not give us directions one way or the other. In that case, we could say it's approximately 2.02. For us, as you do the practice problems in this chapter, or one more chapter after the exam, what we might need to do is to work backwards. If they give a standard error in a couple questions, we might need to work backwards to reconstruct what's the standard deviation. All that would take would be to multiply both sides by the square root of n to get rid of your denominator, and then s would be alone. So we might run across that once or twice before finishing the semester, depending on the examples I pick. Any questions so far? All right. Then let's look at 18.3b, which is on page 440. Part B. Use table C to find the critical value, in other words, T star, for a 98% confidence interval if, let's see, I believe when they put the T comma 26, they may have already subtracted 1. Let me see if I can find evidence of that. Just in case, let's pretend that they're telling us that the sample size is 27. Then your degrees of freedom would be 1 less than that. Which I think, based on the fact that they wrote T parentheses 26, they probably already subtracted the 1 is my guess. So taking a look at table C, do we have, on that left-hand column, do we have somewhere where there are 26 degrees of freedom listed? Is that one of the things listed on the left-hand column? Yeah? Right here. Follow that row. Instead of looking down at the Z star row now and finding what's underneath 98%, you have to, if you know N, find your degrees of freedom, look in that row and where that intersects with 98%. And let's see if I can keep my hands steady here. 2.479? How many agree with that? Okay. So that would be T star equals 2.479. Questions?
What happens if the number isn't on it?
That's a good question. First, let's address something else, and then get to that. Then we'll follow from it. For any column, whether it's the 98% column, or any column, look what happens as you work your way back up. Look from Z star, work your way up that same column. These have bigger degrees of freedom, which mean bigger samples. What's happening to these values in this column? They're getting bigger. Any of the columns that would work out that way. If you're working your way back towards smaller samples and smaller degrees of freedom, your T star gets bigger. What's that going to do to your confidence interval? What would it do to your margin of error? If T star is bigger. Bigger margin of error. And so your confidence interval is going to be wider than if you had a bigger sample with a smaller T star. Bigger sample, bigger degrees of freedom, and therefore smaller T star. Well, the fact is they run out of room. I will show you something here in a bit where we could use the calculator. There was a normal CEF. There's a TCEF that I'll show you how to use here in a bit. But if you're going to use the table approach, remember I was talking about not politically, but statistically being conservative, then let's say, for example, your sample size is 500. How many degrees of freedom do you have? For a sample size of n equals 500, 499 degrees of freedom. If we want a 90% confidence interval, which is this column, if 499 degrees of freedom isn't there, go up to a lower degree of freedom for a lower sample. You're playing it conservative because it'll make the confidence interval have a bigger margin of error, wider confidence interval then. You're playing it conservative, trying to capture mu. And it'll have the same effect on the hypothesis testing then. By working that way, moving up. If you don't have that 499 in there, work your way up. Then, if we follow that approach, we will hopefully avoid rejecting H0 when in fact we should not have it. We're playing it conservative. Does that help answer the question, Neil?
Yeah.
Okay. I actually had it on one of the slides, but it doesn't necessarily come up in the same order that I typed it. So, good question. All right. Let's take a look at 18.7. We're going to take the information in 18.7 and deal with it two ways. Make a confidence interval as requested, and then in a later question they use the same data. Do a hypothesis test. So I want you to see here how much is staying the same to what we've been working a few weeks on versus the minor tweaking just because we don't know sigma and we're using S instead. So in 14.7, here's the question I was telling you about a week or so ago. I thought it was in chapter 15, but I guess not. Ancient era. The composition of the Earth's atmosphere may have changed over time. To try to discover the nature of the atmosphere long ago, we can examine the gas and bubbles inside ancient amber. And when I told some of you I was looking for this question a week or so ago, I was reminded of Jurassic Park, where they got dino DNA out of amber. Anybody remember me talking about that? No? Who does? Remember, Brooke? Junior? Okay. All right. So, amber is tree resin that is hardened and trapped in rocks, blah, blah, blah. Okay. Gas and bubbles within amber should be a sample of the atmosphere at the time the amber was formed. Measurements specimens of amber from the late Cretaceous, which I think was before the Jurassic, but I can't. Nope, it might have been the period after the Jurassic. But anyway, so they measured the oxygen in a sample of amber, and I'm going to put this in the calculator because they don't tell us X bar or even S. So, let's see here. Do you remember what button we have to press to be able to enter in data? Stat. Okay. And we'll go to the very first option there. Edits. Our first one is a 63.4. What's our next one? After the 63.4. Somebody have a textbook handy?
65.0.
65.0?
Yeah.
Okay. Next one?
64.4.
64.4.
63.3.
63.3.
54.8.
54.8.
64.5.
64.5.
60.8.
60.8.
49.1.
49.1.
And 51.
51.0 or it's 51. Okay, so what's the sample size?
9.
9 of them? Okay. So this is 18.7 on page 443. And it's 9. I've read this question already, but tell me something. Of the two, which procedure have you found easier? Confidence intervals or hypothesis testing? Is there one that you would find easier than the other? I would think people find doing the confidence intervals easier. Even the calculations, the idea and the calculations is probably a little easier to work with. And that's what they presented first, probably for that reason. It's the same thing here. So we're going to need to work with this. We're going to need X bar and S from that data. We need N. But to get T star, what do we need? What other formula do we have that involves N? So we have 8 degrees of freedom. That's going to tell us what row to look in here in just a moment for the whatever level of confidence we need. But let's get X bar and S from the calculator. We press that again. Where could we get it to calculate X bar and S for us? Which menu do we go to under stat to get X bar and S? Instead of having to do it by hand. Anybody remember? Yep. Very first option, one variable statistics. So X bar, again, I'm not going to round until, if I'm going to round it all, it'll be at the very end. So we've got X bar is 59.5. That's 3 of them. There's a 9 at the end. So that's 4 of them. I'll bet that's, what, 6 eighths in there? Yep. 1, 2, 3, 1, 2, 3. And then S. We don't want a sigma of that variable because this is not a population. It's a sample. So you want the one above it. Careful on that. Our S is 6.255. 28. 6653. So after the data, the authors say, assume that this is a simple random sample. Actually, they haven't been able to obtain all the amber that was formed in the Cretaceous period, so you could ask the question, can we really regard this as representative? Which is why they say it in parentheses, this is not yet agreed upon by whatever scientists would be looking into this type of thing. But then we're supposed to use a 90% confidence interval to estimate the mean percent of nitrogen in ancient air. So that was 90% for the confidence level, right?
Yes.
Okay. Something they didn't tell us is whether we have a normal distribution, or at least is it symmetric and single peaked. What else could we look at on here to get an idea of whether it's symmetric? Besides X bar, what's something we could compare X bar with to tell if maybe it's symmetric? Median? Tiffany had told us that before break, I think. The median is 63.3, which is a little bit higher than what we've got for X bar. It might be skewed left, but hey, this is a pretty small sample. So as before, we're proceeding with some caution. So, let's look for the T star that we need when we have 8 degrees of freedom. Find the 8 degrees of freedom row and the 90% column. What's the T star that we're getting there? $1.860. How many would back that up? Got a few backing you up. That's the one that is right here. And that is in the 8 degrees of freedom row and the 90% column. So T star, 1.860. So when we plug into the formula I had over on the sideboard, we would have the X bar plus or minus the T star times the sigma, not sigma, S. I'm going to run out of room on the board, but I'm going to have the calculator have everything in there. So on the board, I'm just writing that. So I'm running out of space. Here's a very, 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 very important question. What am I dividing by the square root of? What number am I going to put in there? 9. Although degrees of freedom had us subtracting 1, it didn't change what we said about n elsewhere. We still have the 9 there. Okay? Remember, if you're going to do this one step at a time, you would have to take the square root, divide S by that, multiply by the 1.86, that would give you a margin of error. Then you could do X bar minus the margin of error and X bar plus the margin of error. But if you try to add or subtract first and then multiply, that's going against the order of operations. Thing is, the calculator knows the order of operations, so we can type this in all at once. If you would like to be lazy and not type in all of X bar, stat again, second and above stat is list. If I go to the map and mean, tell it the mean of L1 where the data was entered, and subtract to get the lower bound. Now I don't know if I went back to that list stuff, which standard deviation I would try to take, sigma or S. So I'm going to type out all of that. I haven't experimented with that one enough to know. 6.255, 2 8, 6653 times, oh, I forgot to put the 1.86, but the order of multiplication would not matter. So T star times S, or S times T star is going to be the same. So times 1.86 divided by square root of 9. Well, that's 3 anyway. If I were going to give you directions of where to round that, since the readings went at best to the tens place, the furthest I would go, if I was going to round it all, would be to 2 places, to the hundreds. So my lower bound would be 55.71. And my upper bound, switch the minus to a plus. Upper bound of 63.4 what? 47. Okay. If we were doing a two-sided test of H naught, mu equals whatever we have for the percent of nitrogen in our present atmosphere, which is 78.1%. By the way, does anybody back up my calculations? Getting the same thing? Okay. So if we were to say in a two-sided test, either ancient error is no difference versus an alternate hypothesis that mu is different from 78.1, what do you think this would be telling us? That it is different? Or is no different? Ancient error compared to present error. Mu is 78.1% nitrogen right now. That's a percent. What do you think that confidence interval tells us? .1 within the lower and upper bound? No. So even without doing the test, do you think you would reject or fail to reject? Reject H naught in a two-sided test. At what level of alpha? 10%. Your claimed mu is not in there in the confidence interval, and you're doing a two-sided test where C plus alpha equals 100%. Yeah, we would probably reject H naught then. Questions? Okay. Well, the last one we'll do here real quick, and then I'll pass back the homework. Same set of data. Oh, that was 18.3. 18.7 uses the same set of data, though, on page 443. Where we're supposed to do, maybe I got my numbers wrong. Well, let's do a 10% test, even if I have my pages and example numbers wrong. We have null hypothesis that the mu now is no different from the mu back then, population mean of the entire atmosphere, that it was 78.1%. This would actually give me evidence to do, with a different sample, test whether it's less than actually, because both of those are less than the 78.1, but to make the comparison to a two-sided confidence interval, let's do a two-sided test. Calculating our T is just like calculating Z, except that in place of sigma, we have S. Remember, it's not U minus X bar. It's always X bar minus U. Or in this case, the plain view, mu naught. S we had was this. And just like I said on the last one, even though degrees of freedom had n minus 1, in the rest of it, it's just n. So divide by the square root of 9 here. You can put parentheses around the numerator, and parentheses around the denominator, and then round to 3 places. So, mean of list 1, or type in that 59 point blah 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 all the way to the end. Minus our claimed mean of 78.1. They're all in percents, so you don't need to make any conversions there. Divided by parentheses around the mini fraction, 6.25528 6653. That's getting divided by the square root of 9. That one's a nice perfect square, so divided by 3. Oops, the division symbol to show up. See if somebody can back up my calculation here. I'm getting negative 0.878 when I round to 3 places out. Anybody getting the same? Chelsea?
Yeah.
Joshua? Okay. Here's what we do. Back in the confidence interval, we had 8 degrees of freedom. We still want to use that same row in table C. Let me bring up the screen here. As we discussed before, and you had to do at least once on the homework, if you had a negative z-score, because of symmetry, we had to drop the negative, take the absolute value. So I'm looking for an 8 degrees of freedom. They keep getting bigger as I go left to right. So 8.878 is bigger than all of them. What do you think that tells us about our probability then in a two-sided test?
There's like 99.99.
Okay, that would be for confidence interval. Flip side, if you go down to that last one that we compared to, 0.001 or 0.1%, because 99.9% plus 0.1% will give you 100%. So our p-value, remember the switch in directions, will be less than 0.001 or 0.1%. What was our alpha? 10%. Reject H naught or fail to reject H naught? Michael? I think you said it. No. Okay, we've got P that is less than alpha though.
Essentially reject.
So when it's less than or even equal to, reject H naught. Remember the interpretation then. That means you have found significant evidence. You have found significant evidence that in fact, for the whole atmosphere, the population mean of nitrogen is 78.1%, is different from 78.1%. And that agrees with what some of you were telling me about the confidence interval. Since 78.1 was bigger than even the other round, was outside it. So you're expecting in a two-sided test that you're going to reject the null hypothesis. That's what we want to do. When you have a one-sided test, comparing a confidence interval, all bets are off. You only make that comparison, confidence intervals, two-sided tests. Alright, get things handed back super quick. Joshua, 2 things for you. Adrian? Whoa. Sheena? Joshua, could you put the website down for me? Kevin? Yeah. Alex? Okay, sorry. Ken? Diane?
For question number 2, check out the thing I attached on the back.
Abel? Chelsea? You're kind of halfway here. All yours, I think. Make sure that nobody else is stuck together with yours. Michael? Mackenzie? Awesome. Jalen Garcia? 15? Dakota was not here today? Alex, was Dakota not behind you today? Thanks, sorry, hey, Krista. And if you leave, but don't make that change. Aloha. Delta.
That's it. I'll bring a personal fan in next time. Yeah, bring a fan next time.
You also be willing to buy one that's about this big for $50 from Big Lots
Maybe.
and have it circulate? But actually, really, there's no kind of rules if you bring in a small one that you have just facing your face. I can't think of any rules that would prevent that. As long as it doesn't make noise that would stop us from hearing, which I can't imagine a small one doing.